Hello, and thanks for tuning in again. In this lecture, we're going to talk about the Lewis acid-base concept. The Lewis acid-base concept is named after Gilbert Newton Lewis, who was a very famous American physical chemist. He's the same Lewis that also introduced the Lewis structures that you have already encountered in the lecture. Now, previously, we have learned about the Bronsted acid-base concept. And in the Bronsted acid-base concept, the species of concern is the proton. So you remember that a Bronsted acid is a proton donor and a Bronsted base is the proton acceptor. Now in the Lewis acid-base concept, this is quite different. Here the species of concern is the electron, or to be more precise, the electron pair. A Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. The reaction of a Lewis acid with a Lewis base leads to the formation of an acid-base adduct, which is also called a donor-acceptor complex. Now this is quite different from the Bronsted acid-base theory again, whereby an acid-base reaction would actually lead to a conjugate acid-base pair. An example for a Lewis acid-base reaction is depicted here. And so we are looking at a proton that reacts with a hydroxide anion to form water. Now in this case, the proton carries a positive charge and is therefore the electron acceptor. The hydroxide ion carries a negative charge and therefore it uses this lone pair to donate to the proton. So it acts as the electron donor and therefore the Lewis base. The product of this reaction is the water molecule, and you can see that both Lewis acid and Lewis base are incorporated into a single moiety. So this is your Lewis acid-base adduct. A second example is shown on the bottom here and involves the reaction of a pyridine molecule with HCl. In this case, the Lewis base is the pyridine molecule because it carries a lone pair, and it utilizes this lone pair to donate to actually the proton of this HCl molecule. After reaction, you have a pyridinium ion which forms, and that again is your Lewis acid-base adduct. And you have a chloride anion left, which simply balances the charge of this adduct. Now again, to clarify the roles of the species in this reaction, we need to understand that the HCl itself is not the Lewis acid. It is a Lewis acid donor, so it provides the proton, which is the Lewis acid. So the proton accepts the lone pair of the Lewis base from the pyridine and forms therefore this adduct. Now, in addition to reaction with protons as Lewis acid, pyridines can react with a wide variety of metal ions. Here we show an example involving nickel 2+ as a metal ion. So all metal ions can be considered Lewis acid because they are positively charged. And in this particular example, 4 equivalents of pyridine would react with 1 equivalent of nickel 2+ cation to form a tetracoordinated species, which is the complex or the adduct. Now, since the pyridine molecules are neutral, the overall charge of 2+ in this complex must come from the 2+ charge from the metal ion used. In coordination chemistry, the Lewis base is called a ligand. So coordination chemistry is nothing else than Lewis acid-base chemistry. And a complex or coordination compound consists of a metal center which is surrounded by a specific number of ligands. The metal centers are the Lewis acids, and the ligands are the Lewis bases because they use their lone pair to donate to the metal center. Now the Lewis bases can be neutral or anionic, and they bind to the central metal using a specific atom which is called the donor atom. There are various types of different donor atoms that are applicable. For example, you can even have a hydrogen or a hydride. You have carbon, nitrogen, oxygen, etc., as donor atoms. And the number of ligands that bind to a metal center is called the coordination number. This slide shows examples of Lewis acids and Lewis bases. Now, since Lewis acids are electron pair acceptor, it is good for them to carry a positive charge. So you have various metal ions that function as Lewis acid. These can be alkali metal ions, alkaline earth metal ions, and transition metal ions. In addition, you can also have neutral molecules that do not fulfill the octet rule. For example, you have BF3 or BeCl2. On the other hand, Lewis bases are electron donors. So they should carry either a negative charge, which makes them better donors, or they could also be neutral species with lone pairs. So anions such as hydroxide or oxide, several halides, sulfides, selenides, etc., can be very good Lewis bases. You also have pseudohalides like the azide anion or cyanide anion, and you can also have neutral molecules which carry lone pairs. A water molecule, for example, carries a lone pair, and we have seen examples of Lewis acid-base adducts containing water already. If you remember back, the aqua acids are essentially Lewis acid-base adduct. In addition to water, you have nitrogen-based compounds such as amines, ammonia, phosphorus-based compounds like phosphines. You have also arsines, etc., and so the number of Lewis bases and Lewis acids are immense. Now here we will look at several examples of acid-base reactions involving metal ions. The first example we have encountered already before. And so when you take a copper salt and you dissolve it in water, 6 occurrence of water will actually bind to the copper 2+ cation, and you will form this hexa-aqua complex. Now this hexa-aqua complex is your Lewis acid-base adduct, but we have encountered it as an aqua acid. So you can remember that if the species donates protons, then it would actually act as an aqua acid. In this particular example, we are treating this hexa-aqua complex with chlorides, and you actually have a ligand exchange. And so the 6 water molecules will be replaced by 4 chloridoligands. And so you form a new compound, which is called a tetrachloridocuprate. Now this particular species is greenish yellow, whereas the hexa-aqua species is actually blue. So the coordination chemistry has actually many examples of very colorful compounds. This reaction, which we call a ligand exchange reaction, is also a Lewis acid-base reaction. So the Lewis base is the chloride that brings in its lone pair, and the Lewis acid is the copper ion again. You can also create this tetrachloridocuprate complex directly by mixing copper 2+ ions with a chloride source. Now the reason why the coordination number changes in this case, so you change from a coordination number of 6 to a coordination number of 4, is due to the charges of the ligands. Water molecules are neutral, and so you can actually bind many of the water molecules around a copper ion without essentially changing its positive charge. The chloride anions, on the other hand, are negatively charged. And so if you would put 5 chloride ligands around the copper, you will have a buildup of negative charge. So the system stops with 4 chloridoligands because it has already built up a negative charge of 2-. Another example is shown here. We can have a silver 1 cation, which reacts with 2 equivalents of ammonia to form a diamine silver complex, which is colorless. In addition to metal ions, we also have neutral molecules that can act as Lewis acids. Here you can see beryllium chloride, and if you apply the electron counting to that, you will realize that this species is only a 4-electron species. So it does not fulfill the octet rule, which means electronically this species is unsaturated. And because it's unsaturated, in its solid state, it would actually form a polymer, and in this polymer, all the beryllium atoms are bridged to the next neighboring one via chlorido bonds. So the polymerization of barium 2 chloride to form the polymer is in itself already a Lewis acid-base reaction. If you give the system additional chloridoligands, it will happily cleave this polymer and accept the 2 additional chlorides to form this tetrachlorido species, which carries a 2- charge. So here is a model of this particular compound. You can also add other Lewis bases into that. And here we have an example involving diethyl ether. Now in this diethyl ether molecule, the oxygen, which is bridging 2 ether groups here, still carries 2 lone pairs. We do not draw these lone pairs, but if you know how to do the electron count, you should be aware that there are 2 lone pairs available at this oxygen. Now the diethyl ether molecule utilizes the lone pairs, or one of these lone pairs, to donate to the beryllium, which is void of electrons, and it forms the adduct, which is the diethyl ether adduct of beryllium chloride. So these are examples for Lewis acid-base reactions involving a Lewis acid of group 2. We have here examples of Lewis acid from group 13. Group 13 contains boron species, aluminum, gallium, indium, and thallium, and each of them can have 3 substituents, which can be a halide, an alkyl, or a hydride. And all these species, if you do again your electron count, are only 6 electron species. So they would like to take in 2 more electrons to fulfill the octet rule. And they can do this by reacting with a Lewis base. And in this particular example, we have trimethyl boron as a Lewis acid, and it reacts with ammonia as a Lewis base because the ammonia still carries a lone pair at the nitrogen. And so the nitrogen donor atom would interact with the boron central atom of the Lewis acid to form a borane ammonia complex or a borane ammonia adduct. Now, the interesting thing here is that before the reaction, the boron Lewis acid is actually trigonal planar in geometry. And so the hybridization of the boron is sp2. And the Lewis base is already sp3 hybridized because we will take into account, of course, the lone pair. So this is already tetrahedral in shape. And so a sp2 species reacts with the sp3 hybridized species to form an adduct. And in this adduct, if you look at the boron, it has changed its hybridization from sp2 to sp3. The geometry around the boron is tetrahedral now. The nitrogen has retained its sp3 hybridization. So again, upon Lewis acid-base reaction, a rehybridization takes place whereby an sp2 Lewis acid is converted to an sp3 hybridized Lewis acid-base adduct. In this slide, you can see aluminum chloride as an example. Similar to barium chloride that we have seen before, aluminum chloride is unsaturated in terms of electron count. Now, due to its unsaturation, it has 6 valence electrons. It would dimerize to form this hexachloridoaluminum dimer. So if you offered a Lewis base which can actually provide electrons to saturate the octet fulfillment, then the reaction would take place, and acetonitrile in this particular example would cleave this dimer and become the 4th ligand to stabilize the aluminum species now in this particular adduct, and the aluminum has now fulfilled its octet. Similarly, you can also have gallium hydrides here. They are also electron deficient, and they react with trimethylamine to form an adduct. And in the gallium case, you can also react with 2 equivalents of trimethylamine to form a pentacoordinate species. Now this one has more than 8 electrons in its valence shell. The most famous Lewis acids from group 13 are actually derived from boron. We have seen already an example of trimethyl boron, but here we will be looking at boron halides. And obviously in terms of halides, you have boron fluoride, you have boron chloride and boron bromide, and also barium iodide. So these only differ in the halogen atoms. And of course, all of these 4 examples can react with a Lewis base to form a tetrahedral species. And we have seen that already. So this reaction again occurs via rehybridization from sp2 to sp3. Now the Lewis acidity of these 4 species increase in the following order, whereby boron trifluoride is actually the weakest Lewis acid, and the boron tribromide or triiodide would be the strongest Lewis acids. Now, in terms of electronegativity of the halogen atoms, this conclusion is rather unexpected. And this is so because fluoride or fluorine, as we know, is the most electronegative element. And intuitively, the boron trifluoride should have the least amount of electrons at the boron center because it's bound to the most electronegative fluorine atoms. Therefore, it should form theoretically the strongest Lewis acid. However, this is not the case. And the reason behind that is that we have to consider something which is called pi donation from the halide to the boron. And the ability to donate pi electrons to the boron is actually increasing from fluoride over chloride to bromide. Now this is depicted here. So here we have an example of pi donation. As you know, each of the halides would still contain 3 lone pairs after it's bound to the boron. And each of these lone pairs can actually overlap with the boron to form a partial double bond in this case. The question is, why does fluoride, being the most electronegative, actually is a better pi donor compared to the chloride or the bromide? Now this has to do with the size of the fluorine atoms with respect to the boron. Now boron and fluorine have the most similar sizes, and therefore their orbitals are also of similar size. And so they are best equipped for an overlap of their orbitals. And so fluorine becomes the best donor, although it is still the most electronegative element. Now, if you increase the size from the fluorine atom to a chlorine atom or even to a bromine atom, then the orbitals at the halide will become bigger and bigger, and so the orbital overlap with the boron is less efficient. That is the reason why the order of pi donation decreases in this particular order. If we move to group 14 acids, then we encounter this very famous molecule, which is carbon dioxide. So carbon dioxide has actually already fulfilled its octet. So reaction of carbon dioxide with an hydroxide anion as a Lewis base would lead to a formation of a bicarbonate anion. Now in this particular case, you have not an expansion beyond 8 electrons, but you have an octet rearrangement. So the negative charge that comes from the hydroxide anion actually is donated to the central carbon, and one of these double bonds would flip out to form the negative charge of one of the oxygens that were initially double bonded. So of course this is just a resonance form. The negative charge can also be delocalized to the other oxygen, and essentially the two oxygen would have the same bond distances to the carbon. With silicon fluoride, you have an octet expansion, so you can react it with one fluoride or two fluorides to form a penta or hexa coordinate species. Of course, with the reaction involving two fluoride anions, you would form an octahedral complex, which is 2- in charge. And this species is hypervalent. And I believe you have discussed hypervalency already in your first part of the module. In group 15, we have elements like nitrogen or phosphorus. These elements are actually known to form Lewis bases in general, but there are also a few examples of Lewis acids that are based on these central atoms. Here we can see an example, which is phosphorus pentachloride. So phosphorus pentachloride, as mentioned here, is a monomer in the gas phase, but when you condense it down to a solid, it will form actually an ionic compound by itself. So you have two molecules of phosphorus pentachloride in the gas phase, and upon cooling down and condensation, there is a reaction occurring whereby one of these molecules would act as a Lewis acid. And so it would accept a chloride anion, which is liberated from the second molecule of such. So you have again a Lewis acid base reaction occurring to form a new adduct, which is this hexachloridophosphor species. With antimony fluoride, you have a similar reaction, and in this particular case, the pentafluoride species receives a fluoride anion to form a hexafluorido species. Now this species is your Lewis acid base adduct. But because you are actually treating the species with two equivalents of HF, one of the HF will accept the proton from the second one to form H2F plus cation. Now this compound or this salt in general is known as a superacid. Since HF is already a typical Bronsted acid, which is strong, you could actually convert via this reaction the HF molecule into a H2F cation. And of course, this H2F cation will be very happy to lose its proton, and so it becomes a superacid. So again, in summary, by conducting a Lewis acid base reaction, you're actually creating a super Bronsted acid. Here we have another example containing a very similar Lewis acid base adduct. Again, we have your pentafluoro antimone species, which receives a fluoride as a Lewis base to form the hexafluorido species. Now, in this particular case, this BRF3 loses a fluoride, and of course, it loses a negative charge, and what remains is a BRF2 cation. So since we are talking about superacids, we also need to define what is meant by superacids and superbases. Superacids are more efficient proton donors than anhydrous sulfuric acid. Now, in this particular example, when we refer to superacids, we are referring to proton donors, and so you realize that the superacids refer to actually Bronsted acids. We have seen our example already, the combination of H2F with this hexafluorido antimonate. And this particular species is a 10 to the power of 16 times stronger acid than sulfuric acid, which is already among the mineral acids one of the strongest ones. You have another example here, HSO3, and again you have the same Lewis acid-base adduct contained in this magic acid. And again, because of that stabilization of this hexafluoro species, the proton here is very weakly bound to the sulfur element, and so it can be easily removed. So these superacids can even protonate alkanes, and alkanes are very inert in general. So methane is a very stable molecule, but you can even protonate it to a CH5 cation using these kind of superacids. So what are superbases? Now, superbases are more efficient proton acceptors than the hydroxide ion. For example, you have lithium nitride, and more commonly you can have these metal hydrides, which include sodium hydride and calcium hydride. And in these metal hydrides, the H atom carries actually a negative charge. So you have Na plus combined with the H minus. And of course, H minus is a very strong base, and it would like to grab a proton under formation of dihydrogen. So when you release these other species in water, they always form the hydroxide anion. And the lithium nitride can even deprotonate dihydrogen. If we move to group 16, then we even encounter less examples of Lewis acids. So most group 16 compounds are actually Lewis bases, but there are a few examples. And one example is the SO3 molecule. Now this SO3 molecule is a strong Lewis acid, and it can react with amines of this general formula to form the respective adduct. So this is not really difficult to understand. All you have is a lone pair donation from the amine to the electron deficient sulfur center of the SO3 molecule. Now it is also known that dissolving SO3 in water leads to the formation of sulfuric acid. In fact, that is the production process of sulfuric acid. With the knowledge of Lewis acid-base chemistry, you should be able to express this reaction in terms of a Lewis acid-base reaction between these two partners. Another example of a sulfur-based Lewis acid is depicted here. So you have a sulfur which is bound to 4 fluoride substituents. And in this particular case, this species has even a lone pair, but it can still accept an additional fluoride to form a pentafluorido species. And in this pentafluorido species, the sulfur has simply accepted the lone pair of the fluoride while retaining its own lone pair. So obviously, the whole species will become negatively charged. And the ammonium moiety here is simply a cation that balances the negative charge of this Lewis acid-base adduct. So overall, the lone pair at sulfur is retained, since fluoride is a Lewis base that donates a lone pair to sulfur. In group 17, we have the group of the halogens. Now, the halogens can actually form compounds which can be described by Lewis acid-base chemistry as well. You have an example here involving diiodine, and this I2 molecule can react with an iodide to form a new anion, which is the triiodide anion. So in this particular case, a neutral Lewis acid reacts with the negatively charged Lewis base to form a new adduct, which is the triiodide anion. You can have also a more elaborate example containing a combination of an iodine and a chlorine atom. And in this case, it reacts with a chloride anion to form a dichloride iodoanion. Here we have a third example of an hypervalent iodine species, which still carries 2 lone pairs, but the 2 lone pairs also in this case are retained upon reception of an additional Lewis base, and so you end up with this tetrachlorido species, whereby the central iodine atom still contains 2 lone pairs. Finally, we go to group 18, and group 18 is actually the group of the noble gases, so they are actually not really reactive. But Lewis acid-base chemistry also can happen with elements from this group. Here we have an example of xenon oxide that reacts with a fluoride as a very strong Lewis base to form a new adduct. You have also xenon hexafluoride that again reacts with the fluoride to form a 7-coordinate species. And so the structure of this unusual species is depicted here. You have 7 fluoride atoms surrounding the central xenon atom. If you would connect all the fluoride atoms together, then you have this geometry, which is called a capped octahedral structure. Having discussed so many examples of Lewis acids, let's focus on Lewis bases now. In group 14, you have Lewis bases that are derived from alkanes. And so if you take an alkane and deprotonate it, you would actually get an alkyl anion, which carries a negative charge and a lone pair. And so these alkyl anions can bind to, for example, transition metals. And that particular alkyl anion would form complexes which we call organometallic compounds. You can also have other carbon-based Lewis bases. And here is an example of a phenyl anion, which is derived from formal deprotonation of benzene. So if you take a benzene molecule and you remove one of the 6 protons, then obviously you retain a lone pair and a negative charge here, and it can utilize this deprotonated carbon as a donor atom to bind to Lewis acids. In group 15, we have very common Lewis bases. And you have examples of anionic bases, and you have also examples of neutral bases. Most of you will have encountered amines already. So these are typical amine compounds, whereby the most simple example would be ammonia, where the R groups are all hydrogen atoms. But if you replace the hydrogen atom with alkyl groups, then you can have primary, secondary, and tertiary amines. And all of these species would contain a lone pair. And so it can utilize this lone pair to coordinate to Lewis acids. Now, if you remove one of the R groups, then you have 2 lone pairs left at the nitrogen, and you can actually derive that species formally from deprotonation of a secondary amine. So a secondary amine has the formula R2NH. If you remove this proton, obviously you will get a negative charge here, and you have 2 lone pairs to donate to Lewis acids. Now, in analogy to the nitrogen species, you have the phosphorus and arsenic species, and these are called phosphine and phosphide, arsenes and arsenide. But other than that, the structures and the chemistry are very similar to those of the nitrogen species. All of these species are containing the central atom, in this case nitrogen, phosphorus, or arsenic, in an sp3 hybridized mode. If we move to group 16, again, we will encounter very common Lewis bases. And if we look at the neutral species, then we already know water as a ligand, which is called aqua, or we can have alcohols that can coordinate, or we have ether that can also coordinate. And all of these examples, we have 2 lone pairs at the oxygen that are not drawn. If we remove a hydrogen or a proton from water, we get the hydroxide. If we deprotonate an alcohol, then we get an alkoxide, and we install a negative charge here. So now these become anionic, and of course, having a greater negative charge here, they are better electron donors than the neutral versions. You can remove the second proton from a hydroxide, and you get an oxide, and that oxide is now 2- in charge, and so it is even a better Lewis base. You can do the same kind of chemistry with sulfur analogs. So you have hydrogen sulfide, or you have the thiol, or you have the respective thioether. So the chemistry is very similar to the oxygen, and the compounds are also very analogous. And you can also have selenium analogs, and the chemistry again is very similar. In group 70, we have Lewis bases, which are the typical halides. So we have seen many examples where fluoride or chloride or bromide acts as a Lewis acid, and they can form adduct with all sorts of Lewis acids. In addition, we have pseudohalides like this azide ion or the cyanide ion or the thiocyanate or the cyanide ion. And all these species can coordinate and bind to metal ions. The thiocyanate and the cyanate anions are special because the negative charge can either reside on the sulfur or the nitrogen. And so these species can either bind to the sulfur or they can bind via the nitrogen atom. So two different products can be obtained in a Lewis acid-base reaction. Now we also have organic molecules that can act as Lewis bases. We have seen already an example involving pyridine. We have furanes, we have thiophenes, and we have nitrogen heterocycles with a 5-member ring, and this example is a pyrrole. And you can see here all of them contain lone pairs, and obviously since they have lone pairs, they can potentially act as Lewis bases. Now you can have also examples in which the Lewis base has actually two reactive centers. In this example, we have ethylene diamine, which is this particular molecule. And ethylene diamine, as the name suggests, contains actually two amine functions. Now you can see each of these amine functions contains a lone pair, and they can actually bind to a metal center in a bidentate fashion. Bidentate fashion means both of the nitrogen can actually bind to the same metal ion. You have nitrate anion, which can bind via the oxygen atoms here, and formerly, the nitrate anion, which is derived from deprotonation of a nitric acid, has a 1 negative charge. But in this resonance structure, you can see that the positive charge is at the nitrogen, which is balanced by one of the negative charge oxygen, and so there is 1 negative charge left. Other bidentate species would be an oxalate anion containing 2 oxygen donors, or you can also have a carbonate ion, which also has 2 sites for interaction with Lewis acids. And the last example is the thiocyanate ion, which still contains a lone pair here at this nitrogen, and it has lone pairs at the sulfurs. So potentially it can actually bind to 2 different metal ions as Lewis acids. So with these examples, we close this lecture. From the many examples seen today, you can already conclude that the Lewis acid-base concept is applicable to many different areas of chemistry. It is a very important concept, and again, to get a feel for that, I encourage you to look into all these examples and try to understand them in detail again.